Okay, guys, ready? All right. Well, the good news is I'm going to teach you a shortcut for evaluating definite integrals like that. Obviously, up to now, the only thing I showed you is how to use the limit definition with the limit of the summation and all that. Good news, I'm not going to make you use that again. From here on out, you can use the shortcut that I'm about to show you. Okay? All right, so how do we evaluate a definite integral like that? Well, the shortcut I've been talking about is called the second fundamental theorem of calculus. Now, again, don't really worry about the name because actually some textbooks call this the first fundamental theorem of calculus, so don't even worry about the name.
Hi, it's Alex because his birthday.
She also got rid of her crutches for her birthday, too.
Good job. She was supposed to take them up tomorrow, just so you know.
Ah. What? All right, so here's the deal, guys. Now, by the way, this only works if f is what? Continuous from A to B. Just keep that in mind. It's not going to be an issue too often, but just understand that, you know, that does have to be the case. All right. So here you go. What you're going to do here is you're going to take the antiderivative of little f. And the antiderivative we usually call big F, don't we? So when you take the antiderivative of little f, you get big F. And then what you're going to do after that is you're going to plug in the upper limit into your antiderivative and subtract what you get when you plug in your lower limit into your antiderivative. And obviously you'll get a numeric answer when you do that. And that'll be the value of the definite integral. Got it? Okay. So, by the way, if f is the antiderivative, big F is the antiderivative of little f, that's another way of saying that what? Big F prime is the same as what? Little f. Okay, it goes both ways, obviously. Okay, so in words, this is what you're going to do. Take the antiderivative of little f, leave off the constant. The reason you can leave off the constant is, suppose you had a c in here. Aren't you going to subtract the same c in here? So the c's are going to cancel each other out anyway, so don't even bother to put it. Got it? So when you're doing a definite integral, you don't even need to bother to put in the c because they'd cancel out anyway. Okay? So again, just take the antiderivative of little f, put in the upper limit b, and then subtract what you get when you put in the lower limit a. Pretty easy, right? Okay, here's an example. So you evaluate that definite integral. I'm going to take the antiderivative of that, which, again, shouldn't I just use the power rule? By adding 1 to the exponent, divide by your new exponent. And by the way, this is the notation. This is a proper notation. After you take the antiderivative, put it in brackets like that. Copy the limits like that. Okay, that's just standard notation that I want you to do. And then from there, you stick in the upper limit of 4 and subtract what you get when you stick in the lower limit of 2. And obviously, after simplifying, you get your answer. Told you it was easy, right? Got it? All right, so let's do this one here. I don't know. Anthony. So what would I do here? Okay, that gives you what? Okay, good. Oops. And again, you don't need the c when you're doing a definite integral. Okay, then just put that. And then I'm sticking the upper limit. And subtract what I get when I stick in the lower limit. Everybody agree that's what I get? When I stick in the upper limit and then subtract what I get? Let me say again. I stick in the upper limit and subtract what I get when I stick in the lower limit. Isn't that what I get? Okay? You can double check me on that, but I'm pretty sure that's it. Okay. And so at this point, this simplifies to what? Negative 4. And then minus a half minus 3. So you get what? Negative 7.5, which is what? Negative 15 halves? Either one. Okay. Any questions on that? We good? Okay. Now, here's another example I typed up for you so I could go through it quickly. Obviously, if I want to integrate that, I'm going to have to write it in exponent form, right? So I can use the power rule for antiderivatives. Everybody see what I did there? And then from there, the power rule again says you add 1 to the exponent, divide by your new exponent. Simplify that to this. And by the way, you should all know that the square root of x to the 5th simplifies. Doesn't it simplify to that? Okay, everybody with me? And then from there, I just stick in the upper limit of 4, and then subtract what I get when I stick in the lower limit of 1. And again, I think you see why I'm making you simplify these radicals, because if you don't simplify the radicals, good luck sticking a 4 in there. Would you want to stick a 4 into there and raise it to the 5th power, then have to take the square root of all that? Would you? No. So now you see why I've been making you simplify your radicals. Is that clear? Okay, so just finish it up. You get that, which, by the way, turns into 62/5. All right. All right, James, can you help me on this one here? Again, don't I need to integrate that? So what's the antiderivative of sine? Negative cosine. Good. Everybody agree with that? Okay, and then what? What do I do from here to Kuo? Yeah, so what do I plug in first? Yeah, plug in the upper limit, which is pi. And then subtract what I get when I plug in what? Pi over 4. And be careful with these subtractions and the negatives. That's why you got to use brackets on these, okay? Just to be careful. All right, so what's the cosine of pi, guys? -1. And what's the cosine of pi over 4, guys? Square root of 2 over 2. Okay, so after simplifying all that, I get 1 plus square root of 2 over 2. And if you get a common denominator, you end up with 2 plus the square root of 2 all over 2. Agreed? Okay. Any questions before we flip the page? Are we good? Any questions? Ryan, is this okay? Okay. Okay, Erica, on this one. How do we find the antiderivative? What do you got to do first? Rewrite it as what?
Put the x on top.
Yep.
X to
Okay, good. And then once you do that, we can just use the power rule, right? Okay, so what's the antiderivative if you add 1 to the exponent and divide by your new exponent? Okay, good. And then, by the way, this simplifies to this, doesn't it? Right, guys? Agreed? And then you can stick in the 5, and again, subtract what you get when you stick in the 2. Again, be careful with the negatives. So obviously that turns into -1/5 plus a half, right? And isn't the common denominator going to be 10 here, right? So you get -2/10 plus 5/10, which is what? 3/10. Any questions on that one? Again, be very careful with all the negatives and the subtraction, and make sure you do it in the right order. You put in the upper limit first, then subtract what you get, and you stick in the lower limit, right? Any questions? Okay. Careful on this one. Samya, how do I integrate that thing? Yeah, it's the natural log one, right? So you get the, what, natural log of, yeah, absolute value of x, right? Don't forget the absolute value, right? Everybody agree? Okay. And then what do I do from there, Hope?
you plug in
The e, okay.
and subtract it with the 1 function.
Okay. Now, obviously, the absolute value of e is just e, isn't it? And the absolute value of 1 is just 1, isn't it? Okay, and then what is the ln of e, guys? 1. And what's the ln of 1? 0. Somebody agree you get 1 there? Okay. All right, now, let me warn you about example 7. And I kind of skipped over this on the last two examples so I can back up a minute. Let me ask you, is 1 over x squared continuous from 2 to 5, guys? Is it? Are there any discontinuities? Well, what's the only discontinuity there? 0. But is 0 between 2 and 5? No. So do you agree that that was continuous on the interval, so it was okay to get that answer? Okay, what about this? Where's that discontinuous? At what? 0 again. But is 0 between 1 and e? No. So that one was okay. What about here? What's the discontinuity here? 0. Is 0 between negative 2 and 1? Yes, it is. So the integral does not exist. By the way, if you went through the same process I went through here, you'd get an answer. You would think it does have a value, but that answer is invalid. Got it? Right? So just be aware of that. So if I wrote that like this, like I did back in example 5, it would have worked. I would have gotten a number, but that number would be invalid because the function is not continuous on the interval. You understand how you got to just be careful about that? Okay? So I guess what I'm saying is this. If there's a variable in the denominator, you better check to make sure the function's continuous before you continue. Got it? Okay. That's kind of funny. Make sure it's continuous before you continue. Okay. Okay. All right, so here we go. All right, be careful here, guys. All right, so obviously I'm going to integrate. Narek, what's the antiderivative of 2? 2x, okay. Okay, how about this one? Andrew, what's the antiderivative of cosecant squared? Think to your derivative rules. Yep. Negative cotangent x? Okay. Everybody agree? The antiderivative of cosecant squared is negative cotangent x? Because remember, since the derivative of cotangent is negative cosecant squared, going backwards, isn't the antiderivative of cosecant squared negative cotangent, right? Okay. Okay. And by the way, we can turn this into this, can't we? Okay. All right, now from here, what do I do, Allie? What do I do from here? Yeah, which one first? Careful. Pi over 2. Yeah, don't you plug in the upper limit first, right? Okay. Okay. Now remember, cotangent is the same as what? Cosine over what? Sine? All right. What's the cosine of pi over 2, guys? 0 over the sine of pi over 2, which is what? 1. So don't you get 0 over 1, which is just 0? Everybody agree? Okay. Here, what's the cosine of pi over 4? Square root of 2 over 2. What's the sine of pi over 4? Square root of 2 over 2. So that's just what? 1. And so be careful here. I get pi minus pi over 2 minus 1, don't I? It's very easy to mess that up, so be careful. And then we get a common denominator to make it 2 pi over 2 minus pi over 2 minus 1 over 2, which gives me what? Pi minus 1 over 2. Is that right? Is that right? Oh, 2 over 2, sorry. So it's pi minus 2 over 2? Yes? Yes or no? Sorry about that. Good. All right. Any questions? All right. All right. Let's see. Alex, can you help me here? Obviously, I can't integrate a quotient, right? There's no quotient rule for integrals, so can I do something to that first using algebra 1? What would you do? Write it as what? Yeah. So basically, you split it up as x cubed over x plus 1 over x, which then turned into x squared plus 1 over x. Everybody agree we should do that algebra 1 first? Yes? All right, now we need to integrate. So Adam G, how do I integrate that? What do I get?
You're going to get 3x over 3.
Say that again.
I mean, x cubed over 3.
Over 3. And then plus, what's it? Yep. ln, f, don't forget the absolute value of x, right? Okay. And again, you don't put the plus c on the definite integrals because they would cancel out even if you did, right? Okay. All right, so from here, obviously, we're going to stick in the 4. And then subtract what we get when we stick in the 2. Sorry, I know I'm getting writing kind of small there. And so at this point, we get this. And then I'm just going to rearrange things. By the way, you guys, can I write that as ln of 2 squared, can I? Isn't 4 the same as 2 squared? So I can write it as ln of 2 squared, and then what am I allowed to do with that 2? I can what? Yeah, I can bring it out front according to one of your log properties from Algebra 2, right? Can I? So at this point, that gives me what? 56/3. What's 2 ln of 2 minus 1 ln of 2? 1 ln of 2? So again, when you see something like ln of 4, start thinking of simplifying that, right? By writing 4 as 2 squared so you can bring down the exponent. Got that? So what would ln of 9 turn into, for example? Yeah, well, you'd write it as ln of 3 squared and then change that to what? 2 ln of 3, right? Got it? What would ln of 25 turn into? 2 ln of 5, right? Got it? Okay? All right, so obviously that's necessary when you're, when you're trying to simplify it and also when you're taking a multiple choice test that, where you need to get one of the correct answers, right? Okay. All right, now we're going to do a little more with this by asking you to find the area of the enclosed region between this graph and the x-axis. So first thing you're going to do is graph it. Everybody agree with that? Okay. And so can somebody describe what this looks like? Max, what does the graph of that look like? Can you describe it real quick?
It's a parabola that opens down.
Yep.
It's just 1 up from the
Okay, good. And so that's going to be the vertex, right? And it's going to open downward. And by the way, you can quickly do the math in your head. What are the x-intercepts going to be? 1 and -1. Okay? So everybody agree that's what my function looks like? And then I want to find the area of the enclosed region between that graph and the x-axis, right? So we're talking about this, aren't we? Isn't that the area we want to find? Everybody agree? All right. Okay, so how about Kevin? Can you write an integral then for that area? That red area is going to be found by doing what? By integrating what? Okay, good. Everybody see what he did? He just looked at the region and he picked out that you'd be integrating from -1 for that, from -1 to 1 for that region. Does that make sense? So does everybody agree that the value of that integral will give you the area of that shaded region there? Okay? All right, so let's do it. You know what? Let's not do it. I'm confident you can finish, okay? But, all right, I wanted to at least do that step. By the way, real quick, is there another way I could have done that? Because of symmetry, what could I have done? Couldn't I have just integrated from 0 to 1 and then doubled my answer by multiplying it by 2? Wouldn't that have been a little bit easier? Why is it a little bit easier? Because it's easier to stick a 0 into a function than it is to stick a -1 into a function. So that's just another option. It would have made it a little bit easier. Is everybody aware of that? Yes? Okay. It's not really a circle, though. It's a parabola. It's not a circle. It's not. It's not a circle. It looks kind of like it, but it's not. Got it? Okay. Yeah, that's a parabola function, not a circular function, right? Okay.
So if the top is 1 unit up and if the sides are 1 unit over.
It doesn't mean that this is circular in here. It doesn't mean that.
Okay, it doesn't have the same circumference.
Okay. Okay. No way. Is this the last page? Wow. Okay. All right. Do you remember these? I made you memorize them for the last test. Yes? Did you? Or did you get them wrong? Well, here they are again. If there's another chance to get it right on this next test. Got it? Okay. So the antiderivative of that is inverse sine, right? The antiderivative of that is inverse tangent. Okay. So then, for something like this, didn't we talk about the fact that if you have a constant inside of an integral, if you like, you can pull out the constant? Didn't I say that in the past with one of our properties? So can I pull out that 3 if I want? Okay. All right, it just makes the inside simpler, doesn't it? Okay, now. So what is the antiderivative of that, guys? Right there. What is it? What is it? Inverse tangent. Okay. All right, now, obviously you're going to put in your upper limit, right? Now be careful here. You put in your upper limit and then subtract what you get when you put in your lower limit, right, guys? All right, now let's talk about this. I'll wait for you to write it down so we can talk about this. Okay. All right, now if you remember what an inverse trig function is, like that, for example, that is asking you what angle theta results in a tangent value of 1. Isn't that what it's asking you? And so I think you guys can do that in your head. When will the tangent, which by the way is sine over cosine, turn out to be 1? Well, when the sine and cosine are the same. And where does that happen at? It happens at a reference angle of pi over 4, doesn't it? Assuming sine and cosine have the same value, yes? So now wait a minute. There are some limitations if you remember when you learned about the arc trig functions back in Algebra 2 or pre-calc. The inverse or arc tangent function is only defined from negative pi over 2 to pi over 2. Is that clear? So whatever angle you give me here, whoops, sorry. Whatever angle you give me here, it better be in between negative pi over 2 and pi over 2. Is that clear? And again, what else did we say? It has to have a reference angle of what? Pi over 4. And what else? Sine and cosine both have to have the same sign, right? They have to both be positive, both be negative. So could the answer be down here in this quadrant, or no? No, because they're what? Cosine and sine have opposite signs, don't they, right? Cosine's positive, but sine's negative, so it can't be there. So doesn't it have to be in the first quadrant, guys? Doesn't it? And so what is it? Just pi over 4? Everybody agree? Okay, let's do the same thing here. This is asking you what angle theta results in a tangent value of 0. Well, remember, tangent is sine over cosine, isn't it? So you'd have to have 0 over 1, wouldn't you, in that case? Where does that happen? At 0, right? Yes? And so clearly that's the only possible answer, isn't it? For that one? Okay? With me, Anthony? With me? Heads up for me? Heads up, please. All right. And so what's my answer here, guys? 3 pi over 4. All right, let's do this one. All right, Anthony, this will help keep you awake. What is the antiderivative of that thing right there? Inverse sine, okay? All right, now, at this point, again, I've said it about 10 times at least, we plug in the upper limit, subtract what we get when we put in the lower limit, right? Here it goes. Okay, again, now you have to familiarize yourself with the limitations on the arc sign. And so on the arc sign, you can only have an answer, again, between negative pi over 2 and pi over 2. Same thing, right? So with that in mind, what's the reference angle that results in a sine value of square root of 2 over 2, guys? What is it? Pi over 4. Now, this is positive, isn't it? Isn't that a positive value? And so in which these two quadrants is sine positive, the top or bottom? Top. And so it's got to be there, again, with a reference angle of pi over 4, doesn't it? You with me? Yes? So isn't it just pi over 4? And then, again, look at that. At what reference angle does the sine turn out to be a half, guys? Yeah, pi over 6, right? And since that's positive, don't you have to be in the first quadrant again? So isn't that just pi over 6? And obviously I need a common denominator to combine these. So isn't it going to be 12 for the common denominator? So what is this? 3 pi over 4, what's this? 2 pi over 12, so what do you get? Pi over 12. Very good. Okay. Any questions? Almost done. Okay, everybody come get a calculator if you don't have one. And I mean everybody. Everybody. Make sure you get one that works. I know my batteries are starting to go on those. Make sure you get one that works. All right. You guys, I want you to pay attention to this because your calculator cannot evaluate an indefinite integral, but it can evaluate a definite integral. So what I'm saying there is if I asked you to find this, which is obviously this, right? Calculator is not going to tell you that. okay? So you can't do an indefinite integral. But if I gave you something like this, which is obviously a numeric answer, the calculator will do that for you. It will give you a definite integral, but it will not give you an indefinite integral. Is that clear? Unless you have a TI-89. But anyway, you don't go out and buy one. Trust me. They designed the AP test to not give those students any advantage, so you don't need it. Okay? All right, TI-83 is fine. All right, or TI-84, whatever. All right, so you understand what your calculator can and cannot do? Yes? Okay, so. All right, so it can do a definite integral, and this is how you do it. Ready? There's two ways. There's a home screen method and there's a graph screen method. Ready? Let's do the home screen method first. And let's just go ahead and do this, right? Ready? All right, so here's what you do. On the home screen, you hit the alpha button, then you hit the window button, and then you choose number 4, which is what? Function integrate. FNINT stands for function integrate. You following me? Choose that. And look how nice it looks. Everything shows up and it's obvious what you do from here, right? What do you put there? -2. Then you move up here with your arrow button. You put in a what? 1. Then you put what here? X to the third minus 5x. And what do you put here? X. And then you hit what? Enter. Easy. Yes? Got it, guys? Okay. All right. Now you could also have done that on the graph screen instead if you wanted. And so here's how you do it. Ready? Okay. We can do the same one on the graph screen, or we can do a different one. Let's just do a different one. Doesn't matter. Okay. So, all right. Let me just show you. Okay. And then I'll let you do the last one. Let me just redo the same problem, guys. This time I'm going to do it on the graph screen. Ready? Okay, so I'm doing example 13 again, this time on the graph screen. Ready? So I'm going to graph it by hitting Zoom Z standard. And then I'm going to do the following. How do I do it on the graph screen, guys? I hit what? Second trace, which is actually second calc, right? Got it? So hit second trace. Number 7, right? You see the integral symbol? That's obviously what you want, isn't it? Following me? Now wait. What's going to happen is you're going to go back to the graph screen, and it's going to ask you for the lower limit. So what are you going to put in? -2, and then just hit enter. Then it's going to ask you for the upper limit. So what are you going to type in? 1, and then hit enter. And not only is it going to give you the answer, it's going to show you the shaded region. Got it? It is fancy, very fancy. Okay, good. All right, so I want you to try, why don't you do example 14 both ways, guys, just so I know you can do it. So why don't you do example 14 on your own both ways real quick. Do it on the home screen and then do it on the graph screen. What's that? For what? The next one? I don't know, whatever it says. I'm not sure. Because you use that for the subtraction button instead of that. I mean, it should be the same, but it's not. You all right over there, Jeffrey? You okay? Oh yeah, make sure you're in radian mode. That'll give you incorrect answers as well. Always make sure you're in radian mode. Done? You all right? All right, ready? Okay, so let's do it on the home screen first. So I hit alpha window number 4 and just type everything in. By the way, where's the fraction button for that? Anyone know where the fraction button is? Where is it? Alpha, y equals, option 1, right? And then just type in pi, type in the 4, and then you got your tangent x. Be careful with the parentheses, minus e to the x. Okay, does that look good to everybody? Is that what you got? Yes? Okay. All right, now let's do it on the graph screen. And when there's a trig function involved, I'd like to start by hitting zoom what? Z trig. Yeah, try and use the trig window when there's a trig function involved, right? It usually works out nicer to start with, right? All right, now I'm going to integrate this by doing what again? Second trace, or second calc, that's right, number 7. And then lower limit, I'm just going to type in 0 and hit enter. Upper limit, I'm going to type in what? Pi divided by 4, yes, hit enter. There you go. I get the same answer either way. Are we good, guys? All right.